that the Italians have an official program in cold fusion, and that actually organizing group is not mentioned here, but the sponsors of the meeting include the Italian Physical Society, the Consiglio Nazionale del Research, I guess that's a national consortium research, and IFN, the Istituto Nazionale di Fisica Nuclear Physics Institute. And the website where you can get information about it is right here. And of course you can contact me if you're more interested. There are a number of other things that are coming out. In May or June, there is going to be a special issue of an ethics and science journal titled Accountability and Research. It's going to be devoted to cold fusion. Now, part of what's going on here, I sincerely believe, is that there has been a serious breakdown. Actually, I was the editor of this, so or the special guest editor of this. So what happened was we accumulated papers dealing with the question not whether or not cold fusion was right or wrong, but how the method worked and whether. And there was an important conclusion that came out of that, which is that there wasn't sufficient debate. Things got cut off too soon. There were mistakes made. Hans and Fleischmann, of course, made a lot of mistakes. They did. But, for example, forums like this forum got caught up in the problem, too. There was a very confrontational environment that occurred on May 1, 1989. And immediately after that, it was like, the end of a lot of stuff. I mean, and there was a lot of just confrontation. The basic point is that a forum like this one is a very vibrant forum where debate should go on. Scientific debate should go on. These are very contentious issues. And prematurely, that was one of the major conclusions. So it wasn't whether cold fusion was right or wrong. It was, did the process work? The conclusion was it has not worked. People are not hearing about what's going on in the field. And there's another interesting book called Excess Heat by Charles Baudet that is being distributed through, actually this is a cottage industry. There is a magazine, Infinite Energy magazine, that has actually developed as a result of the lack of information getting out. And Mallove, who is the editor of this magazine, is here, and he will be speaking and had wonderful information about what's been going on. And he is the first point of contact for Charles Baudet's book. And the website is there. Now, there's a very polarized situation. There are lots of debates. There are lots of things that are unknown. And I think it is important to recognize that a forum like this one is the place to get these things out. Bob Park, for example, recommended 5 years ago that we start doing this. And we're doing it. And that's how this is done.
I think I might make the announcements, guy. I have one.
Sure.
The winter AMS meeting in Washington, D.C. in November will have a special session on this topic as part of the isotopes and radiation division. Maybe I can just pass some of these areas around.
Absolutely.
Thanks.
Absolutely. Check out these. This website is an interesting one. It's interesting. The Italians are going after this in a very interesting way, and that should be very interesting. All right. Okay. My name is Scott Chubb, and I work for the record, I do work at the Naval Research Laboratory, and we are interested in getting to the truth. We're interested in finding out what's going on with this stuff. I'm going to be giving the first talk. The rules of the session are there's a 2-minute warning. Talks go for 10 minutes. You can actually go to 12, but it's at 12 I cut you off, or whoever is doing the timing cuts you off. So we ideally want to have 2 minutes of questions, and we want to keep on schedule. Okay. With that, I will give the timer to you, and I'll do it for 8 minutes.
That make a point?
Yeah.
It's not technically 2:30.
Oh, okay. We'll wait.
It's conceivable that someone.
We'll wait. We'll wait. Okay. Yeah. All right. Yeah. Keep it open for a minute.
Your timer, by the way, has started though.
Yeah, I'll get it. I'll get it to correct it.
The timer just walked out the door. We need to pay attention to it.
Thanks a lot. Cut off my time, huh? Well, I'll just dig into Rodman's time. Time is all relative. All right, well, what time is it now? Now, all right, you want to give me 8 minutes?
8 or 10?
2:28. My watch is fast.
I'll bid you 227.
2:30, I think.
Do we hear you ask the console Calvin to do timing for you? Perhaps I should take over timing?
That's relevant.
He's also a fair guy. All right, you ready? 8 minutes? All right. I'm going to give one of several theory talks that are presented here. I give what I call a theoretical basis for anomalous heat and helium-4 deuterium-metal systems. An important point is that I'm going to be talking about a coherent type of process, which goes along, is consistent with measurements that have been made. There are going to be other talks that are going to be focusing on, they make use of coherent type phenomena too, but they're different. So I'm going to talk about the problem of unconventional physics, motivation physics for what I call getting outside the box, which is related to what I mean by unconventional physics. So more exact physics, and then the ion band state theory and general nuclear ion band states. Now what I mean by getting outside the box is we have what we know is true, or we believe by general consensus to be true, and then outside the box is what we suspect might be true. Now, some people, for example, Bob Hart, refer to this as voodoo science, and I think that is just a term. Just think of it as a term. I'm going to suggest that actually, we're right here. We actually can we are close to understanding the relationship between being inside and outside the box. That you can account for things based upon the known laws of physics, although people haven't recognized that as a general rule. Now, what do we know in particular? Well, inside the box, we have these. I've depicted these reactions.
Can you stand further aside, Scott?
Okay. What we have are proton and a neutron, proton, and we have the two of them coming together, forming what's an excited state of helium-4, and decaying off into helium-3 and a neutron, or tritium, a proton. These reactions in conventional nuclear physics ignore electromagnetism. They are separable. They are on different energy scales. The electromagnetic and the nuclear reactions essentially can be treated that way. There's a second reaction that hardly ever occurs in free space, where electromagnetics is critical, and that's where it just goes into helium-4. Now, the point is, the electromagnetic interaction penetrates to all length scales. If you're going to, for example, go to a scenario where you want to actually couple to a solid, I've depicted it here, you're going to have to be making use of electromagnetics. Now, the reason is, well, first of all, our knowledge of these reactions is actually outside of a solid. And a solid typically has momentum scales and length scales where the reactions occur of 10 to the 9th electron volts per C. This is a factor of 10 to the 5th greater than the types of momenta that one sees in the solid. In other words, you're talking about angstrom scale here, Fermi scales here. The basic point is, though, that electromagnetic interaction does penetrate to those scales. So conventionally, they don't talk to each other, but an electromagnetic interaction possibly could make them do it. Now, the motivation, well, what I'm going to argue is that the wave properties of solid-state physics do actually allow this to happen. That in particular, it's possible for many small amounts of momentum to be coherently distributed and taken up by the solid, and through processes that are that allow this to happen. So the nuclear and atomic scales can talk to each other. It's reminiscent of the Moskvar effect, and it's actually a very fundamental aspect of solid-state physics. I'm going to talk about the more exact equations. There are exact equations, multiple scattering equations, that formalize this kind of picture, but I'm going to give a little motivational physics behind it that a lot of people don't really think about very much, and has been part of the source of confusion. In particular, electromagnetic interactions penetrate all length scales, but a common assumption that people make is that momentum is equal to mass times velocity. It is not mass times velocity. which is mass over charge times current. Current is momentum minus E over CA, which can also be written in the form of something that people involved with superconductivity know about, but it's actually a more general expression. It's the expectation value of the gradient of the many-body phase, wave function phase, minus E squared over mc times the vector potential. Now, in most situations, this doesn't really make much difference, but it does make a difference when you have situations where the momentum over one particular region and the vector potential have different properties. In particular, when the current vanishes over a boundary, and you get this type of condition, and you have a situation where the gradient of the phase is zero. For example, on here, you can get a superconducting type effect and a Meissner effect outside. More generally, that kind of phenomenon also can be used to account for lattice reflow. And the types of effects I show here, Meissner effect, spontaneous lattice reflow, as in Mossbar effect, Umklapp processes, and so forth. Important points are that it usually is unimportant because appreciable numbers of particles must share or approximately share the common phase, requires appropriate interaction timescale, finite excitation gaps usually applies to ground state type configurations. Boundaries are necessary. And broken gauge symmetry only has to be approximate, and that's important. In particular, if one goes back and thinks about the exact reaction theory, what one means by reaction theory, as opposed to starting out with some kind of gamma factor or something that nuclear physicists do right away, you go to the basic definitions. You get back to a form that's usually not very useful, but it's exact. The point is that this functional form can be related to a non-local problem that gets back to how I mentioned the fact that you have these wave-particle properties in solids. In particular, the equations are actually fairly well known. They go under, there's a book out on this, and I won't bore you with details, but they go under the idea of multiple scattering theory, the new wrinkle to multiple scattering theory that I'm going to suggest that we're going to use. Multiple scattering theory involves converting that matrix element type thing into a bunch of derivatives at singular points. These derivatives can become discontinuous. These are points where the potential becomes infinite. These kinds of things are actually all very well known, and they go under the generic idea of Kringa-Cohn-Rostocker method, multiple scattering theory. The new wrinkle that I'm going to suggest in implementing these kinds of things is that what we typically do in these types of methods is we approximately match a wave function onto an exact solution in another region of space, and another wave function over here. And the basic point is, rather than do it with conventional atomic type calculation, what one does, you see, is one has a particular problem here. One solves a problem here. One solves a problem here. One solves a problem here. One performs a kind of approximate matching that allows for transfers of momentum at the individual location. And all I'm going to do is I'm going to say we're going to replace the atomic with nuclear. So we calculate nuclear wave functions, do a matching of electrostatic wave functions on the boundaries, and proceed. And there's nothing wrong with this. It is just that people haven't thought of the idea that you would have to couple the nuclear to the electromagnetic length scales. So, the result of this kind of construct is illuminating. This was basically what looked like a Fermi-Golden rule type expression. And what it is, all that was sitting in here was a B, a potential operator. When you convert it to multiple scattering, you use the exact wave function, and you use gradients, and you have them at the boundaries where you have large changes, potentially large changes in momentum. That was 8 minutes, right? In many situations, this gives you a very large expression. Now, to have coupling to anything inside the lattice, the scale of reaction has to be comparable to what one sees inside the lattice. So normally, it's virtually impossible for this thing to occur unless you have, sort of high energy processes. However, if you have degeneracy, and this is what gets back to the gauge symmetry idea. By degeneracy, I'm referring to the fact that you have states. Well, first off, you must note that this derivative is a many-body derivative. It involves all of the particles in the problem and all of the possible couplings. Now, the degeneracy I'm talking about, the simplest kind of degeneracy, there could be other ones, but E of k plus G. G is a reciprocal lattice factor equal to E of k. If you have, for example, n unit cells, you have the relationship that then n times n of epsilon k is E of k. And this E of k out of the E down there. And that's a manifestation of degeneracy. It's essentially saying you're maintaining periodic order and you're in lockstep, allowing for these wave transfers. So that's basically the formulation of the idea. And it can be quantified, it can be reduced to numbers. And Talbot will talk about it a little bit. He'll show some concrete stuff associated with how that works. Okay, how much time? I got 2 minutes. Okay, well, I hope that gives some flavor. I wanted to.
I was ready actually to get all kinds of.
Yeah, well, what we did was we turned the problem around. We came up with realistic. We haven't done realistic nuclear wave functions yet. But what we did was we introduced the notion of cusp. See, if you have a large change in momentum, that's mimicked by a discontinuity in the gradient of the wave function, which is actually the kind of thing that people have been using in multiple scattering theory for many years. And so we mimicked the cusp with a set of parameters and did a variational calculation and identified bounds for the size of the crystal that would give rise to the kind of effect that we want to see. So, so it has been reduced to numbers in quotes, but the new wrinkle here is that, in principle, there's a self-consistency problem associated with, if one were to actually use real nuclear wave functions, there's a self-consistency step associated with what the nuclear radius is and how to do the matching. Okay. Well, what Roger has done is made use of this idea of applying cavitation. Cavitation is a phenomenon of bubbles imploding onto a solid. And it's depicted here. What you have is what he calls transient cavitation. This depicts what it looks like as a bubble would collapse. It's a schematic, the last stage of a 40 micron transient cavitating bubble would collapse on the substrate. The bubble contents are in the process of organizing into a low energy high density plasma phase. 1 T plus and E minus in plasma. People have speculated that cavitation could lead to fusion, and what I'm going to point out is that there is evidence. There is important evidence, both in the heat, the amounts of heat, but also the appearance of anomalous amounts of helium, helium-3 and helium-4, and in ways that impinge upon a target foil. There's D2O in here, and the D2O. Then they're bubbles. So the volume of D2O and the reaction volume, well, this gives you the details. I've got some papers. If you, I will leave papers. He's got, I've got 50 copies of the paper that he wrote. And, okay. So here's a picture of what the device looks like. A vacuum-type piezo-driven cavitation reactor for the production of transient cavitation multibubbles. The reactor is machined aluminum concentric pieces that are bolted together. The system containing the metal foil is run for 24 hours, cavitating the D2O at steady-state temperatures, which is pressurized with several atmospheres of argon. The reactor opened after run with a 100 micron type titanium foil. I looked into the reactor, and as you can see, there's some damage there, and so forth. This is a 40 kilohertz input. Now, the thing that is really striking, and I showed this last year in a similar talk, this year I'm going to get into some of the details of SEMs that he's done and so forth that didn't have last year. He's doing things and some additional work, modified work associated with the heat. But what he typically, he'll do these experiments and he can analyze the gases that come out outside the apparatus. And the point to take home here, the two things that are really, really eye-popping He's measuring the concentration of helium parts per million over here. All right, and here's the ambient helium and air that one expects. And, you see that, okay, for a number of these cases with the palladium foil, it's just huge. It's like, factors of 100 more. Other spectacular result, though, the most spectacular is the presence of helium-3. You get significant amounts of helium-3. The naturally occurring abundance of helium-3 is 1 part in 800,000 relative to the helium-4. And here he gets a factor of 190. Either there is absolutely one incredible pump that could not be accounted for by any known physics, or he is seeing a change in the isotopic ratio that would have to be the result of some kind of nuclear process. Now, he has some suspicion, and it's hard to know where that helium-3 comes from. There is a lot of regular protium around, so that there could be a standard proton-deuteron interaction that gives rise to it. But there also is some evidence of tritium. Of course, tritium decays with a rather long half-life to helium-3. And this shows the extrapolation back using the half-life to what he expects. So there is some evidence of the tritium. Now, an interesting, a very amazing thing. I mean, these guys routinely, when they use regular water, they don't get the kind of damage. I showed you this damage. It's really spectacular. They just, they don't get this with regular water. Also, another thing is they'll get this kind of thing with lots of different metals. They'll use silver, they use other ones, they get this kind of phenomenon.
Oxidation.
Well, there's some of that, yeah. But I mean, the stuff melts. They get, and it doesn't. Okay. But anyhow, the point is that when he analyzes the thing, the point is twofold. When he uses regular water, they don't get that kind of effect. And when they routinely can get the thing to melt when they use heavy water. And when they do detailed analysis of the kinds of things that they see, they get this kind of thing. This is a scanning electron microscope, a picture of the surface of a palladium foil. The surface shows ejector sites. They get these ejector sites, these large, here's one scale, here's another scale, and they get these all over the place. And these, when they actually calculate the amounts of metal that are thrown out by this is a lot of energy. And it's, and they get loads of this kind of thing. Sometimes they get evidence of evaporation. The ejector sites of a different nature that are pictured here indicate the ejector was molten as it left the foil. The right photo is an ejector site in a silver foil. Yeah, right got this effect. The left is silver. Left is silver. Yeah, exactly. Look, he's got that mistake. The left is the silver and the right is the palladium. Anyhow, it looks like he's getting these bubbles. These evaporating bubbles. Now he's quantified this. Made estimates, and he's the real expert on this. I'll just show it to you. He's made estimates of. If you're interested, he's made estimates of the. Okay, good. He's made estimates of the amount of fusion events, number of DD fusion events, based upon the ejector population. They've done heat measurements too, but they're hard to do. The thing that's interesting about doing that is this is just looking at an image and you can get it. So it's actually sort of reminiscent of what Pons and Fleshman did with some of their imagery of boil-off phenomenon in calorimetry. So he, has been able to, really make estimates of this kind of thing. Really, I'm not doing him a service. I mean, this is really fantastic work. It's too bad it's not here. It's good for people to get a feeling for it, at least. Okay, so, what one has is a bubble and a jet pictured here just before collapse. And the process is that this comes down and pinches on a metal surface. The input from a low-energy, high-density plasma jet created by collapse of an acoustically generated transient bubble is about 40,000 d diffusion events. The energy distribution of the jet implantation events are relatively close. Many papers, well, they describe the situation for conventional sonoluminescence. They haven't really investigated this kind of point. The information indicates that although the implantation is a process supplies energy, it is not a direct continuation to the ejected mass. The link between input and output energies is somewhere in a highly charged transient D+ volume. So, you can see a lot of it, but not all of it. But they've done mass spectroscopy measurements of trapped gases over cavitation of D2O that show the presence of 10 to the 14th atom of tritium-4 was also found, in some cases, well over ambient in air, like factor 100. There was no long-range radiation found. That's the key point. No long-range radiation.
So we got up to around 500 parts per million of helium-4?
Yes. Yes. 500. Yeah, 550.
You're saying the ratio of helium-3 to helium-4 was 1 to 190?
190. Right. Not 800,000.
Much more helium-3 than helium-4.
Of course there was, yeah.
Much more helium-3 than helium-4.
No, much more helium-4.
The ratio the other way.
Yeah, no, helium-4 to helium-3 was 190.
What is the acoustical trigger? How many?
It was 40 kilohertz.
And they use argon because that's part of the cavitation process, correct? I think the argon is analytic, the great argon is not.
I'm not sure.
Yeah. Oh, yeah, that's part of it.
I'm not the expert. Yeah.
Well, this has apparently been written up somewhere. Where's this from? How do you get a copy of it?
I got paper. I got
He's got 50 copies of the paper.
Oh, you got some of that.
What calorimetry has he done?
He's got a whole bunch of, he's got a rather elaborate calorimetry that he's explored.
Dick, the calorimetry he's done is just Newton cooling calorimetry, and it's very difficult to understand or even believe. But at the moment we have him trying to run his experiment in one of our mass flow calorimeters, so we're trying to get it a bit more robust.
There also is, I don't know how much these cost, but I just brought it for show. He's written up a very nice report for effort. How much is this? How much does this cost?
No. Did you not pass it on?
I can't get that out. I gotta get it back.
You could pay. I remember this work being very highly mentioned in 1993, but as I recall, it was the only paper using this technology, essentially ultrasound triggered cold fusion. Are there any other teams working in this area?
No, there haven't been. And I think part of the reason is that, there was, this is the best. There was stuff that was mentioned that was certainly work done, and they seem to have dropped the efforts. There's what they call the hydrosonic heat pump, and there were things, there was stuff at Lahaina, for example, where they talk about this at Mallove.
One big difficulty with calorimetry was this whole thing. How do you measure the heat input into the system?
Exactly.
And I want to see some details. I've never seen details of all work.
A report.
Unusual eclectic report.
Entitled Low Energy Nuclear Reaction in the London Status Report.
Well, we keep changing the title, it doesn't really matter. I'm just here to provide you with a smorgasbord of ideas and entertainments. Oh, there's one part, we just came in. Good, perfect timing. Yes, we're from New Hampshire, and we do have a real research laboratory with a staff of 4 engineers and scientists, and also a publishing office. So we have the magazine Infinite Energy combined with this lab where we do test devices, and our viewpoint on the field may be a little different than the typical, what we might call actually mainstream cold fusion. Yes, there is such a thing. people working with heavy hydrogen typically in gas phase or liquid phase. There are things such as catalytic fusion, which someone might class with mainstream cold fusion, the kind of stuff that Les Case pioneered. Ordinary water, light hydrogen reactions, George Miley would perhaps prefer to call it low-energy nuclear reactions. Other people in other regimes claim, such as Dr. Mills, claim that this is a hydrino or shrunken hydrogen atom effect. Time will tell on that, obviously. Plasma electrolysis, which tends to go to high voltage with various types of metals, tungsten, steel, carbon, and so forth. One in particular is a type of gas pioneered by VW Research in Colorado, carbohydrogen gas, where you actually have combustion, some kind, underwater, and you produce a rather interesting gas whose total heat properties, combustion value, as well as the heat generated in the production, appear to, in many tests, exceed the electrical and chemical input. Then, of course, there are these water arc explosions by physicists Renaud and Renaud, Peter and Neil, in which capacitor banks are discharged underwater, and what is apparently generated is a cold fog of some kind that is capable of shooting right through quarter-inch aluminum plates. And there are excess energies from those systems too, on the order of 50%. And then, of course, there's a hydrosonic pump, which I heard mentioned, which is a cavitation device.
Is the ground work that connected with Mobile in France?
Excuse me?
Is that connected with Mobile in France?
Okay. Basically, this is the model of those who approach this heretical field. The circumstances of cold fusion are not those of hot fusion. We're talking the solid state, liquid state, and the excess energy liberated in cold fusion is not significantly transferred by radiation. And this was a lecture at MIT in '91, progress report, and it did print the whole lecture in issue 24 of Infinite Energy. Dr. Mitchell Swartz of Jet Energy Technology has done a meta-analysis of the cold fusion literature and finds, contrary to those who say that only a waning band of true believers at swank resorts are doing this, there appears to be a fairly steady increase in the number of papers in this field. But of course, numbers are irrelevant, just a matter of interest. But there are lots of people working, and there are some thousands of readers of our humble magazine, Infinite Energy. Mitch has done a percentage analysis too. This is a paper that he'll be publishing in issue 30 of our magazine. And he shows that an increasing number of these experiments are positive. To some extent that would be expected, since only those who are perfected their experiments get these very highly positive results. In the beginning, obviously, there was a lot of confusion as to even how to do it. I'd just like to bring a few sample peeks into here. Others will discuss these things. But as I look at the evidence for this phenomenon, I certainly point to this paper by Clater, which keeps getting better and better and better. Verification of tritium evolution at low energy through various types of palladium systems. So our national lab has actually confirmed nuclear reactions at low energy. Dr. Storms has, of course, done it too. This paper, all 56 pages of the Journal of High Temperature Society of Japan by Narada and Zhang, is notable. Now, 5,000-hour repeatable runs, 200 to 500 megajoules per cubic centimeter, like the results we just saw from Roger Stringham, helium-4 and helium-3 in anomalous ratio. Catalytic fusion, we were the first, I think, to even see the excess heat, not the excess heat, I should say excess temperature. We did not do calorimetry then on this. Les Case came to our lab and demonstrated his device, the steel oxygen cylinder of World War II with heavy hydrogen in it, prepared with this special catalyst, with its heater underneath, heat activated, and we did in fact see a significant temperature elevation. Much better groups, such as Dr. McCoubrey's group, has actually seen helium and excess heat from this. He'll talk more about it later, but this is the curve, the rather famous curve of, in the system with heavy hydrogen gas, increasing helium-4 concentration, exceeding any possible contamination from the air, and in the control experiment with ordinary hydrogen, no rise in the Vermont.
You know what the relative date of that one was? Was that 98 or 99? Mike
will discuss it, okay? There's Mike's final conclusion, Mike et al.'s final conclusion, and the final TR 104-115. Before every, they have confirmed the work of Fleischmann and Anomalous. This experiment here is one of my favorites. Unfortunately not published in the open literature, but talked about by Dr. Cravens at various meetings. Motorola did test this Patterson power cell, and with a flow rate of 20 milliliters per minute, with ordinary water, lithium sulfate solution, sustained a delta T of 15 degrees centigrade for at least 11 hours with no input power, and a tail off of heat for 3 days. Because he did show, and I'll do you the benefit of showing you the actual Motorola data. This is, not many people have seen this, but there it is. No applied current, delta T of 15 degrees. And that is certainly not a chemical reaction. Water is pretty cool.
As far as I know, that was done with a parasolic pump. It was extremely consistent in its flow.
That's correct. You can feel 20 watts. It's very easy to feel. And NASA did replicate it, despite the fact that they did qualify the results. This is actually the work of Blacklight Power Corporation that they were reproducing. That's been reproduced at Lincoln Lab too. Now our perspective on this is that we need to get demonstration cells out there. What's that, 2 minutes to go? Okay. George Miley at the University of Illinois is working with us, as is John Dash, and he's got some thin film cells with some significant percentage excess power that we want to test. They're on glass, microscope slides, PD, platinum. You'll be hearing more about that, I hope, because we're developing a CBEC envelope calorimeter to the 3,000 junctions. This is just the beginnings of its development. It has some very stable qualities. You lock it all up. And we intend to put either John Dash's cells in there, closed cells, titanium heavy water cells. This is some test resistors being put in. And here it shows very, very high quality 1 millivolt stability in the 230 millivolt result we use. This is far too fast, of course. But we put in a resistor bank of 5 watts on the top and 5 watts on the bottom successively and got very, very close 0.0451 volts per watt sensitivity. And we can talk about that some other time.
The comment is that the CBEC cells, when you put something in there that generates heat, are not affected by the position of the source.
Yeah. Okay, so I get a minute or two after this. This will be of interest to various public relations officers who might be in the audience. I did get a call from the White House, and they asked me to write a memorandum to President Clinton on cold fusion, which I've done. It's submitted, it's in, and it's called The Strange Birth of the Water Fuel Age. The cold fusion miracle was no mistake. It cites the technical literature. It gives the references at the end, and it says, above all, its recommendations, the highest level recommendation, which I think is very reasonable, perhaps even skeptics would agree with this. Mr. President, you need only do one thing now, publicly state that you are going to investigate this matter and then do it. And then there are various sub-recommendations. And for those who wish to see this paper, I'll give you the sample later. Here's the best experiment of all, not in terms of the physics of it, but society is doing an experiment for better or for worse. Ads are out in Science and Chemical and Engineering News. This is an experiment to see whether people with physics degrees, chemical degrees, chemistry degrees, and so forth will take the opportunity to avail themselves of employment at a company for which it is generally recognized that they are not doing anything that's humanly possible. And let me end with a comment. Since Dr. Park is in the audience, he has said that 10 years after the announcement of cold fusion, results are no more persuasive than those of the first weeks. And he says that it crossed the line from foolishness to fraud. And I would consult my great expert on fraud, Gary Taubes, who in the fields of fear, which was an article in the Atlantic Monthly, said, a study in how the selective reporting of the scientific evidence by researchers as well as journalists can generate anxiety at the expense of reality. And perhaps Scott would want to comment on this particular slide. Okay? I'll just put it up there. Thank you. Okay?
All right. I just want to mention some people walked into the room, and don't forget your toothpaste. Well, anyhow, moving on now. I call for the next paper, which is by Mel Miles from New Hydrogen Energy Laboratory. His permanent address is Minneapolis, Waters.
Like Scott mentioned, this is work that was done in Japan. I had a 6-month employment to work there at the New Hydrogen Energy Laboratory in Japan, sponsored by NATO. That's the New Energy Development Organization of Japan. Just an acknowledgement in case I don't get to it. It was sponsored by, like I said, the New Energy Development Organization. I guess that's equivalent to DOE here in the United States. There's a guest researcher, and Dr. Swami was the main person there running the laboratory. Knowledge his help. And all I'm going to do is just briefly summarize various experiments and then focus in on one. They did have the Fleischmann Pons type cells there, where I ran various experiments using some different alloys. This we had success with before in China Lake. This was developed by the Naval Research Laboratory, and it's worked very well in showing the excess heat effect. We tried some co-deposition experiments developed by Stan Spock at the Navy Laboratory in San Diego, and those worked quite well in experiments in Japan. And in Italy, they developed what they call electron migration, and we got excess heat in one of those experiments. So out of 8 Fleischmann Pons experiments, we had excess heat in 6 out of the 8. I took my own calorimetry with me, developed at China Lake, the Naval Air Warfare Center in California, and ran some experiments there. I repeated 2 experiments that I did in China Lake. This one did not give excess power at China Lake. I ran it again in Japan. Also, it did not produce excess power there. I more or less used that as control. This I had success in China Lake, produced excess heat. I ran it again in Japan, and again it produced excess heat. This is mainly what I'm going to come back and talk about. These 2 experiments right here. But I went on and did some small particles, platinum particles, produced excess heat, where platinum particles in exactly the same experiment did not. Note I used a cell that did produce excess power. Next experiment it was a control, and did not produce excess power. This produced excess power. Next experiment it was a control, and did not produce excess power. In case you wondered anything special about cell A and cell B. And then we also used pulse electrolysis, and again got even larger excess heat than that one cell. Now, since I don't have much time today, I've got some handouts. This was a paper presented in Ashley, Italy in October. They had a workshop there, and I have copies of that paper, and I'll be glad to hand that out in just a minute. I just recently had a paper refereed and accepted, and now it's published. I have not seen the published paper yet, but this is in the Journal of Electron Chemistry. All I have is a Frederick Proof copy of that. But it should be in print. It should have been published 29th of February 2000, volume 482, pages 56 to 65. And since I don't want to take these back with me on the plane, I've got some copies of that paper if you want to hand that out. This has been refereed and now published in a scientific journal, that particular paper. Now, I'm just going to talk today about the China Lake calorimetry, not the Fleischmann Pons calorimetry. The China Lake calorimetry is a isoparabolic cell, The platinum cathode is down here, and the platinum cathode filled with the heavy water and LEOD. And in the outside jacket, I had aluminum foil wrapped around it, and packed just with aluminum foil. And the thermistors were outside the cell; they were not inside the cell. They're actually on the outside surface of the cell, T1 and T6. So the difference in some calorimetry is that the thermistor outside cell wall. Now, in 10 minutes, I don't have time to go through the equations, but you can go through this. It's in the paper, and you can show that how the temperatures have changed with time as you run this experiment. Your electrochemical power is going down with time because as you electrolyze away the heavy water, you concentrate the LEOD. And so the solution conductivity is getting greater, so your IR drop, which is a major part of your voltage, decreases with time. So your power is decreasing with time as you electrolyze away because of the increasing conductivity. And so this is the dominant term, the change of power with time. If you don't have excess power, or even if the excess power is steady and not changing, then you get this equation, and the basis of this equation is that because the power you put in is decreasing with time, the temperature should decrease with time under normal conditions. And in most cells, in most cases that's true, except when you have this excess power effect. Now this is the chart recordings that comes out of the recorder, therefore time is increasing on this axis because that's the way exactly how it came out. We had it scanned in the computer. So this is time. This is temperature. The bath temperature is very steady. Bath and room temperature given up here by running from 20 to 25. The cell temperatures, the C cell differed by about 10 degrees, so we have two different scales here. But note the cell that never produced excess power. The temperature is decreasing with time. We increased the current here for calibration. We went from 300 to 320 milliamps just to get a calibration right there. But it comes right back to the same baseline and keeps on decreasing with time. There's a nice straight baseline with the cell temperature going down as the time increases. And that's the normal behavior. That's what you predict by the equations. This cell, in many cases, I want to show you one example, but there are a total of 7 examples. In some cases, we had temperature going up at the time, and it should never have done that, according to the theory, the calculation. But you see, instead of going down, it goes up. So we do the same calibration, the same increasing current here, and then eventually it does start going down for all the time. So basically, this should have been decreasing with time with the same baseline. I have some way to show that. Maybe I just show it on the graph here. It should have been parallel to this other line. It should have been going down about like that under normal conditions with this outside area. But anyway, you can see there's quite a big increase in temperature that takes place here because of that power increase and the temperature goes up. And by the calibration, we calculated about 80 milliwatts of excess power. And there's no way you can explain the temperature increasing like that except by an excess power effect of some sort. You can look at the cell voltage just to make sure there's nothing unusual about the cell voltage. This is the cell that produced the excess power. The voltage is going down with time. Actually, it's going down faster than this one down here. This is the slope, has a bigger slope. The power is actually decreasing faster in this cell than the one that did not produce excess power. This shows the calibration. When you increase the current, of course, the voltage goes up. The cell heats up somewhat, and so when you go back to normal current, the cell now is hotter than it should be, so it overshoots a little bit here before it comes back to the baseline. So this is normal behavior on the cell voltage. Yet we see a strange temperature increase that takes place, and there's no way to explain that except excess power effect. Maybe I went too fast. How much time? Okay. But
Actually, it's in time.
okay. We have probably other examples in the paper I handed out. We show other examples of where this effect took place, so you can look at other figures in the paper. This is a paper from Italy, and if you want to pass that out, it has a little more, has some different details than the published paper. So in summary, we had this anomalous increase in the cell temperature, and it always is only in one cell, cell A, 7 different times. The 2 thymistors, we had 2 thymistors always in the same cell, and they show exactly the same effects. Any little change, the second thymistor show that same change. They track each other almost exactly, so you can't argue a thermistor problem. The excess power was small. This is not a huge effect. This is one problem, I think, in this field. Everybody at first thought we're going to have huge excess power effects, and they overlook small effects, which most effects I've seen are small, 50 to 500 milliwatts. So you have to look for small effects to find the results in this field, in my opinion, in most cases. The excess power results in a graphic manner. This doesn't suddenly come out of nowhere and go way up high. And when it does appear, it kind of appears gradually, then it disappears. Usually when you add heavy water and cool the cell down, it disappears. No clear treatment event was identified, and in the control cell, we always saw normal behavior. The entire experiment is normal behavior for the control cell. Okay, thank you.
Very good. There's time for maybe one question.
Information that Miles his work is going to appear in the next issue of our magazine. I apologize if it's not here. Jed Rockwell writes also about his experiences in Japan. The whole issue of were some rather important positive results in the NHE program, let me say, sidetracked or charitable, hijacked or concealed, as we put it on the cover of the magazine.
Okay, well, there's time for maybe one more question. Mel Miles, of course, has done important work. He and Bush did the seminal work on identification of Helium-4.
Yeah, I would like to follow up with that. 91. In 6 months, we could follow up on that in Japan, so we just did ecstasy in Japan.
Are you doing some water flow calorimetry too, or CVAP calorimetry too?
No, I've never done either of those two types of calorimetry. They didn't have, they had Mercury's type calorimetry in Japan, the NHE. They had that water flow calorimetry there, but they didn't have a CVAP in Japan. No.
All right, well, let's move on now. Yeah, thank you. Then I have now APS now. System, and I do apologize. It's not my fault. Their program had some typos. They had typos in mine. In his address, it's got 2 exclamation points in his address. Mean nothing. But since he's visiting MIT now, it doesn't really matter. But I'm sure you can also write them here. Okay, so KG Sinha from
So, after the abstract submitted in November, I sent the abstract in November.
Right.
My address has changed and what I'm going to talk today, but mostly done at MIT in the university. Random group of people faculty. Now, in my title of my talk, the word no charge is used. The formula form, that is local charge response. But I mean the pair of electrons which are in single state and are closely bound, and they're like one particle particle behaving as a close particle. So the first role of the local pair I used was the phenomenon of superconductivity in 1960. And in high temperature superconductivity also, myself and several other groups have used it. As soon as the cold fusion was reported, I suggested this one of the concepts in regular, but I didn't publish for obvious reasons. I mentioned briefly in the obituary which I wrote to Professor Charles Mack, who was the first person to suggest we only did use for fusion. And a technical paper I wrote in 1999. What are the essential ideas? The essential ideas involve that besides the proton or neutron, there's ionic species D minus or D H minus, or even maybe molecular species DD or HH in the lattice. Now, in solid we know there are different from the gaseous plasma or the stars of the lattice. You have electrons, you have lattice, you have phonons, and nuclei, and retics. So we have to take all these many-body interactions. What we see in solid happening is a macroscopic quantum states of that, or here quantum situation taking place in many-body interactions. So what I call the local charge bosons, or pure electrons, they acquire a high effective mass and reduce ionic size due to interaction with phonons. And these entities are located in internal channels of the reaction material. Electrons shield the nuclear charge, fully verified is reduced. According to me, the important role of the host material is to provide confining potential for the lattice of neutrons or deuterium or and these are essentially located in channels. Channels must be internal to the solid, whether in the form of defects, immediate effects, or essential to the architecture of the system. Now, a few equations. That is, the equations are the electronic Hamiltonian, the lattice Hamiltonian, electron lattice tracking, and the confinement field of the whole matrix. This is a single particle of the electron and somewhere on that side. The side is X, this is spin, and this is a hopping integral from side to side. This is the energy of the phonons, and these are the creation operators, phonons and the lattice. This is the energy of phonon. And taking Einstein oscillator. And this is the important term, the electron-phonon interaction. At any side, the electron is sitting and interacting with the phonons, and this is the dimensionless coupling constant G. So you can transform this away by a suitable canonical transformation. And then all these parameters will be renormalized. The phonon energy will change. And this will be modified, and there will be other important effects. This important effect is this comes to the following. This is the displacement of the lattice because of the strong electron position. This is given by this term. The single parting energy of the electron is reduced by heat. Equal to G squared per minute, and this is coupling constant. Important consequence of this is that the coupling integral is reduced exponential minus square. And this will tend to localize the electron. Another very important consequence, the effective mass becomes ME exponential d by that is ME exponential G square plus G square. The mass of the electron or electron pair is enhanced. Now, when we talk of the pair of electrons in any object, there is the attraction to the nucleus, which forms with the orbital, and there is mutual repulsion of the electron. But then we have this added interaction, electron-phonon interaction. So if electron-phonon interaction is not there, then this is energy, this is zero, this is zero level energy, and U, which is repulsive, is sitting here. But when you take electron-phonon interaction, the energy can be reduced considerably, and that or this energy, this for the negative U, that is, instead of repulsive becomes negative U, repulsive interaction for two electrons. With this of work, 1967 and there was a very important seminal paper written by Peter Accession in physical electricity in 1975. It showed how the Coulomb repulsion, visual Coulomb repulsion of electron, can be reduced considerably because of electron bond drive, and effectively there will be pair atom, and later on myself and people remember when we say extended into even the hydrogen molecules type, two atoms, due to talk and H2 or others. So in effect, since pair of electron behave like goes off, even at a bosonic atom, the pair is sitting on the same atom. If it's holding two atoms in a molecule, then it will be bosonic molecule, whether it's D2 or H2. The essential idea I'm driving that in a solid matrix, this neutron of deuterium or hydrogen, they will form the lattice of this bond. With this mechanically, both field has to work. They must form their own lattice. So now, the essential idea is that we calculate the overlap probability, that is a certain expression, and then these electrons produce a shielding effect. Then you can take the shielding effect and then calculate what is the overlap probability. These are very parameters. So, and this integral, I calculated recently, and this the value of the integral is this much, and therefore overlap probability takes this form. RW is the fixed of the barrier, and this depends on the shielding parameter, and this can be recast in a very convenient form. So, this is the value of screening protection, and this experimental value I took from the experimental Casari for palladium. It's a very high value, and it is experimental show. And this is the value of the bit, which is 4.6 10 centimeter. And then the figure expression can be parameterized, can be written in this form. Mass of the deuterium upon the neutron upon the mass of the electron, RW, RD. This will use both sides of the areas for a pair of electrons, which is defined here. So the effective mass of the pair becomes every time R given on R, which is m times some number times m. So the overlap probability becomes this, which after calculating the mass of mg as electron, it becomes exponential minus 1 So then you can plot this. So, the overlap probability, you can see how many times the mass becomes larger